Hi chemists, just want to talk you through some atomic absorption spectroscopy. Now this is the last subtopic for topic 1 in the Year 12 course. So I just want to quickly, as we kick things off, and I'll just put this over here, go through the learning intentions for this. So this is what we want to know for this subtopic essentially. So we want to know that flame tests and atomic absorption spectroscopy are analytical techniques that can be used to identify elements. And these methods rely on electron transfer between atomic energy levels. So we need to be able to write electron configuration, so that's subshell configuration, for any of the first 38 elements of the periodic table. This video is not going to cover that. This is best looked at using your textbook or some other resources. Explain the effect on the absorption or emission of radiation on the electron configuration of atoms in atoms or ions. So we'll look at that. We're going to look at why some wavelengths of radiation emitted and absorbed by an element are unique to that element. And we're going to be looking at atomic absorption spectroscopy, or AAS, and how it's used for quantitative analysis. Quantitative means we're looking at how much of a particular element might be in a sample. And that involves explaining the principles of AAS, so how it works, and then the construction and use of calibration graphs. So we'll cover that a little bit in this video. All right, so let's get into it. So AAS is a technique for detecting metals and metalloids in samples. So we get a sample obtained from somewhere and we say how much of this specific metal or this metalloid is in the sample. The advantages are it's a reliable analytical technique and it's simple to use. So once you have the machinery, it's able to be conducted really quickly and the graph is able to be analysed really easily. It can analyse over 62 elements, which is a particularly large sample. It also measures concentration of metals in the sample. So we can figure out what's actually in the sample and how much is there in the sample in regards to concentration. So the metals detected by AAS, this is a very poor resolution periodic table, but the elements that are in pink, so the majority of metals and some metalloids as well, like silicon for example, are detectable by AAS. The other ones we need to use a different type of analytical technique. Let me move my head again. There we go. So basically what happens is the sample's broken down into free gaseous atoms. So the sample needs to be heated up. It's exposed to a flame or to high temperatures. We measure the atom's absorption or emission of light, which we'll go into in a minute. And the important thing is that each atom has its own specific spectra. So every atom has electrons in a unique configuration, and the position of those electrons leads it to produce different wavelengths of light when the atoms in the sample are excited. In this case, we're talking about heating things up, which will excite those atoms. So when vaporized, different elements absorb light of specific frequencies. Now, I know you're already watching a video on this, but I have to take the time to plug this video here. I've linked it in your sector lesson. It's about a 20-minute video. It's quite old. It was made in 1993, so don't let the old music turn you off, because it's actually a really good video just showing how the technique works, and it actually shows the machinery and whatnot. So that is a must watch. And then your notes documents in Microsoft Teams has some notes on how an AAS works. So I'm just going to kind of move that over. This is the document I'm referring to because a common exam question is how an AAS works. So this breaks it down. Essentially, you want to have that level of specific detail when you're answering your exam question. Okay. So essentially, in the AAS, we have a hollow cathode lamp, and that lamp is made from a particular metal, and it emits light of a certain frequency. So the metal that we're testing is in the lamp. So if we're testing for magnesium, it's a magnesium cathode lamp. If we're testing for zinc, it's a zinc cathode lamp. I think you get the picture. I don't need to go through all 62 elements because I probably couldn't. Each element requires a different lamp, as I've stated. So you can probably think of a downside to this technique already. If we're testing lots of different metals, we need lots of different lamps. And these lamps are actually quite expensive. So that's a downside. So the light produced by the lamp is passed through the sample to be tested, which is vaporized in a flame. Now this diagram here is obviously a very basic diagram, but we're showing the lamp. These lines are emitted light because, as we know, light only travels in straight lines. You've got a vaporized sample indicated by this kind of round saw looking thing, and we get through a prism. So the easiest way to show a prism is just like the ones you used to use in like year 10 physics class when you're doing your refraction, and the light rays will refract, and that refraction causes the white light to split up into the different colors. And then light of a specific wavelength goes into this part here. And you can't read that down the bottom, but that's called a photo multiplier. The degree of light absorption is proportional to the concentration of metal in the sample. Now, referring back to that Word document that I looked at earlier, proportional means as one increases, the other increases. So what that's saying is the more light that's absorbed, the more metal there is in the sample. So if we're shining light coming from a zinc cathode lamp, and the light getting to the end here is not very much, that means there's lots of zinc metal in the sample. If there's lots of light coming through, that means there's not very much zinc metal in the sample. This is an example of an emission spectrum, so pretty similar to what we were looking at in the previous diagram. You've got the light source, you've got your light passing through. Now, this kind of slit here, what that's doing is it's specifying light of specific wavelengths. It's only letting certain things pass through. Refraction, and then you'll get basically an emission on a photographic plate. So this is an emission spectrum. So basically that's saying that certain elements will produce light of certain wavelengths. We've done flame colors testing, for example. You've seen fireworks before. And if you've got different colors, that's due to different elements, okay? So sodium has your orange light, copper has your greeny blue light. This is why light is being emitted, okay? So it's got to do with electrons. So what we've got here, we've got a few different energy levels. So we've got a low energy level down here, signified by this E1. E2 is the next lowest energy level, and then E3 is a bit higher in terms of energy level. So we've got electron shells here. So we've got shell 1, and that's the lowest energy, 2 and 3. In this example, we've got a ground state electron that's in this shell here. So this shell we're not worried about. So this electron is in ground state. So basically what that means is that's the most stable configuration that's using the least amount of energy. And what's going to happen is energy is going to be absorbed by that atom. So usually through heat, could be electricity, but generally it's absorbing heat. And this ground state electron is going to be excited. It's going to get to its excited state and it jumps up to a higher energy level, this level up here. Now that'll exist in that higher energy state for a fraction of a second. And it's going to go back down to ground state. And when it goes back to ground state, that energy is passed or it's released. So it's transferred to the ground state electron, jumps up. When it's excited, it goes back down, and it's going to release energy in the form of light. And essentially, the difference in those energy levels corresponds to different wavelengths of light. So this jump here could be red light that's released. A different jump from a certain one energy state to another energy state going back down could be corresponding to green light, because different colors are just different wavelengths of light, essentially. So that's how your light is released. And that's important for this technique. This third diagram is looking at atomic absorption spectroscopy, which is what this technique is focused on. So previously we were talking about light being emitted. In this case, we're talking about light being absorbed. Here we've got our metal vapor lamp, and it's releasing light of a radiation that is unique to atoms in the sample. So zinc cathode lamp, wavelengths of light specific to zinc, and then in the sample we've got atoms, so these are just random atoms, but some of them might be zinc atoms. Now the zinc atoms are going to absorb the light with the specific wavelengths for zinc, because that's how the electrons are arranged. So zinc in the sample will absorb the light. Other atoms that are not zinc, so could be heaps of other stuff, they will not absorb the light. And that light will pass through to the detector. So this is signified by 3 lines and then 1. So a bunch of light's being absorbed and the rest will go through to the detector. And then that's how we see how much there is, essentially. So a simplified diagram using some, I guess, a bit poor resolution diagrams. So we've got our lamp, okay? And that contains the element to be analysed. So that's the cathode lamp. Then we've got our sample. Now the sample is liquid and that gets fed into the machine. The machine needs air and it needs fuel because we're going to be burning the sample. So combustion happening and there's that flame. And basically the light is going through that flame. So it's a vaporized sample. And the reason for that is just to get a better spread of those atoms. Next we go through what's called a monochromator, and that selects for the wavelength. So you change the lamp, you need to turn the knob on the monochromator to make sure the wavelength is correct. And that's making sure, it's like a filter, just making sure the certain wavelengths of light get through. Next is the photomultiplier, so that's essentially getting those readings and allowing it to be interpreted by the machine. And then you've got a readout, and the readout is the graph which the chemist will interpret. Very exciting. So what are you going to get? Essentially you're going to get what's called a calibration graph, and this is something that we need to be able to interpret. So this is an example calibration graph. So what we've got is an absorbance reading, so how much of the light was absorbed, and the units of that depending on what you're looking at. Could be ppm. Concentration is ppm. The absorbance could be a different kind of unit. Concentration is generally in parts per million. Again, it depends what the sample is. It could be ppb, could be heaps of different units. But this one's pretty common. So we've got some different points, and then we've got a line of best fit drawn through the points. So what essentially happens here is you load the machine, the AAS machine, with different samples of the analyte you're testing. So this dot here, we had a metal of a specific concentration, and we know what the concentration is. So you're calibrating it. That's why it's called a calibration curve or a calibration graph. So whatever this corresponds to, it was loaded into the machine, and the absorbance reading was read to be this number, and then that's why this point was there. A second sample, third sample, fourth sample, fifth sample. So you do a bunch of samples of known concentration, you get this curve or this graph. Then, if you have a sample that you don't know, you'll find the absorbance reading. Okay, so just say the absorbance reading of an unknown sample was 0.5, and then you would go across. I should probably get a pen tool, shouldn't I? All right, this is not a straight line, so I apologize for this, but let's see how straight I can draw it. Oh, this is bad. You go across, that's really bad. And then you hit the calibration curve. So with my unknown sample, I'd get a 0.5 reading, and then I would, using my ruler, oh, that's really bad. Oh no, we go down, that's really bad. We'll go down to about there, and then that number corresponds to the concentration of the sample. I actually redeemed myself a bit there, I'm pretty happy with that. So that's how you would plot a calibration curve using known samples, and then your unknown sample based on what you've already calibrated it with. So in this case, your graph might not always go through the origin. So if I go back, this one kind of did. So the concentration of 0 was pretty much spot on the 0, but that might not always happen. And the reason for that is there could be some systematic error in the calibration of the machine. So if the equipment is incorrectly calibrated, then it might be giving you a small reading of absorbance when there's actually no sample in there. So if there is an error associated with that, that needs to be taken into account with the calibration curve. So a potential reason for that, or a cause for that, could be the distilled water used to make up the solution. Remember that sample was fed in as a liquid. It could have been contaminated, and that can contaminate the entire apparatus. So the advantages and disadvantages of AAS. Number one advantage, very sensitive, so you can detect small amounts of a metal in a sample. It's very specific, so we can change the cathode lamp for the element to be tested. It's fast, you get the readout in seconds, and it can measure small quantities of metals. Disadvantages: expensive hollow cathode lamp, and you need to store all of them, and the cost. So, in order to, I guess, familiarize yourself with this topic a bit further, please visit the Microsoft Teams page, have a go at some of the practice questions in there, and practice questions in your textbook as well. Thanks very much for listening. I really appreciate it, and I'll see you next time.